Hi everyone, this is Mrs. Meservey, and we're going to be looking at modeling and equation solving today in our review number 2 as we prepare to move into pre-calculus. So modeling a function, we can model a function with numerical values, which is looking at a data table. We can model a function algebraically, looking at the equation, and we can model a function graphically by looking at a graph. So the first thing we're going to do is look at how to model a function numerically. When we're modeling a function numerically, we can look at the table and evaluate the common difference. If the first difference ends up all being the same, which is called constant, then the function is linear. If the common difference, the second common difference, so you evaluate it twice, is a constant, then the function is quadratic. And I'm going to show you an example of a quadratic one in just a moment. And if the third difference is constant, the function is cubic. So let's look at an example. So example 1 is determine the type of function using the common difference, graph and write an equation for the function. We are going to be modeling the numerical, which is the table, the graphical, which is the graph, and the equation, looking at this function. So the table, you can see the input or the independent variable is x, and it's 1, 2, 3, 4, 5. So we have a constant interval. And the y, or the output, is 3, 6, 11, 18, and 27. So the first thing we're going to do is go ahead and take the first difference. We do this by subtracting. 27 subtract 18 is 9. 18 subtract 11 is 7. 11 subtract 6 is 5. And 6 subtract 3 is 3. If I had to predict, you see the pattern 3, 5, 7, 9. If I had to predict the next number in the differences, it would be 1. In the table, that means 3 subtract 1 is 2. And if I back this up, that would be 0. So there's my table. The first difference is not common, 1, 3, 5, 7, 9. So now we will take the second difference. 9 subtract 7 is 2. 7 subtract 5 is 2. 5 subtract 3 is 2. And 3 subtract 1 is 2. The second difference is constant, so we know this function is, you guessed it right, quadratic. Graphically, if I graphically look at it, here are the points plotted from the table, and I can add the point 0, 2. So then what you can do is you can simply use symmetry and fill in points that are symmetrical to the points that you had. And I'll try my best. I'm just figuring out this writing pad, but here is my parabola. Beautiful. Because of symmetry in a quadratic function, we draw the entire function, which is just what we did. Now we're going to write the equation. We know that the the y-intercept is 0, 2. So the parent function is y equals x squared. Because this shifted up 2, the equation is going to be y equals x squared plus 2. Example 2a. In this problem, we're going to use the algebraic model, and we're going to solve this equation. So first thing we want to do is factor out the 2. So f of x equals, we'll factor out the 2, and we get x cubed minus x squared, subtract 4x plus 4. Okay, in place of f of x, we'll put 0. So 0 equals x cubed subtract x squared subtract 4x plus 4. You might be wondering what happened to the 2. I actually divided the 2 out to the other side, and 0 divided by 2 is 0, so that 2 is gone. Now what we're going to do is split the equation. So I'll split it down the middle, and we're going to factor by grouping. So 0 equals, we'll factor out an x squared, x subtract 1 is what's left. Make sure you factor out this negative in the middle with the 4, and we get x subtract 1. Just a reminder, out of these two groups, you can see that we have an x minus 1 in both groups. So we're going to go ahead and factor out that x minus 1. 0 equals x subtract 1 times x squared subtract 4. We're almost done. X squared subtract 4. If you remember, this is a difference of squares. So we're going to factor that as x plus 2, x minus 2. And then we still have the x subtract 1 equals 0. I set each of those factors equal to 0. So x minus 1 equals 0. X plus 2 equals 0. I'll close that. X subtract 2 equals 0. And that's going to give me a positive 1, a negative 2, and a positive 2 for my 3 zeros. Example 2b, we're going to graph example 2a. So the zeros were 1, negative 2, and 2. You can see this graph right here. There's negative 2, there's 1, and there's 2. Then if we look at the end behaviors, here are the ends of the graph. You can see this end behavior is as x approaches negative infinity, f of x is going down to negative infinity. And this end behavior, as x approaches infinity, f of x goes to infinity. And if you recall the leading coefficient test, remember that if the degree is odd, then one end of the graph will go up and the other end will go down. If the leading coefficient is positive, then the right-hand side of the graph will go up and the left-hand side of the graph will go down. So here is the graphical model of example 2b. Example 3, solve the equation algebraically and graphically. So algebraically, how we get rid of that square is we want to just take the square root of both sides. And when you do that, don't forget the plus or minus. The square root and the square cancel each other, so those two cancel, and we're left with x plus 2. So we have x plus 2 is equal to plus or minus 3. When we subtract 2 to both sides, we'll end up with x equals a positive 3 subtract 2 is 1, and a negative 3 subtract 2 is negative 5. So the two zeros are 1 and negative 5. Graphically, you want to set this equal to 0 if you're going to solve using a graph. Take 9 and subtract it to the left side. X plus 2 squared subtract 9 equals 0. Then in your graphing calculator, you can go to y equals and you can graph this. If you don't have a graphing calculator, I recommend you go to Desmos. Here's Desmos. You can put in the equation f of x equals x plus 2 squared subtract 9. You can graph it, and here you can see there's a 0 at negative 5 and there's a 0 at 1. Example 4, we're going to solve by graphing using your graphing calculator or Desmos. We're going to explore hidden behavior. So if this is to the third degree, that means there will either be 3 real zeros. So under the real, we're going to either have 3 real and 0 imaginary, or we will have 1 real and 2 imaginary, because imaginaries always have to come in pairs. So we know that the degree is 3. So go ahead and go to your graphing calculator and graph it, or go to Desmos. Desmos, there's this little keyboard right here. It pops up, and when you want to go to the 3rd power, you're going to use this a raised to the b, just a little tip. Now, if you're on your graphing calculator, you're going to see a standard window of left 10 and right 10. And we have 2 zeros. We have a 0 right here. And so the first 0 is negative 1.262. And the second 0 is 0.566. And in a different lesson, we'll go over how to calculate those zeros on the calculator. Now, because we only see 2 zeros, we know that there's really 3 zeros that are real. And so you're going to want to expand your window on Desmos. If I can move, I think you can move this screen over so you can see more. And then I've got a 0 here, a 0 here, and then a 0 that's 11.195. So those are the 3 real zeros, and there's no imaginary zeros. So in your notes, if you want to write this down, we're going to end up having 3 real zeros and no imaginary zeros. So our choices, we picked this one. And let's look at the solutions. So the solutions will be x equals negative 1.262. We have positive 0.566 and 11.195. In this class, we will round everything 3 digits past the decimal in order to get ready for